Our next opportunity here in the symposium is a lightning talk number 3. One of our professors, Romilla Pradhan, from the Information Technology Department here in Purdue, and she's going to talk debugging and explaining unfairness in machine learning models. Romilla, great to have you.
All righty, cool. I think that green button will go. Yeah. Okay, welcome everyone, and thank you for being here. After that wonderful discussion on, why it is important to have trust in AI-based systems, I am here to talk a little bit more about debugging those systems and talking about fairness and unfairness in those systems and what we can do. How can we debug those instances of unfairness, right? So which one is next? Okay, so this is next. All right. So we have been using algorithmic decision making in a lot of our domains, right? And they have been used in high stakes decision making. And these sophisticated machine learning models, they have been quite accurate. They have been very popular. They have been very effective in a lot of these domains. However, there has been a growing concern that, all right, I'm figuring out. There has been a growing concern that these models are not interpretable. They are not transparent because a lot of times they are very complicated or they are proprietary in nature, right? So there is a need to try to understand what is happening, right? So as end users, as different stakeholders of the system, we would want to understand what is happening with the system. And it becomes all the more important when there are various biases inherent in the AI-based systems. And you all must have come across these examples where there are biases in, for example, hiring, where it has been shown that there were some systems that were biased against females, against different genders. In healthcare, biases were there with respect to different races. In mortgage approval algorithms, biases were seen with respect to races, and in even your facial recognition systems. And perhaps the most popular example was in criminal justice, where there was a system that was being used in the courts, and it was found to be biased against different races, right? So with all of these talk, explainable AI emerged as a brand new field a couple of years ago, where the idea was to go from that top diagram, and this is courtesy DARPA from 5 years ago, where the idea was to go from that top diagram where we have a machine learning based or AI based system that gives us some output and we don't understand how it performs, why it does what it does, to coming to this place where we have some explainable interface, where we have some understanding of why the model works the way it does, why the model is generating some output, why the model is failing when we trust it, and all of those things, right? So the idea of explainable AI was to generate explanations for different stakeholders of the system, right? Beginning with machine learning developers who build those systems, to machine learning practitioners who use those systems without knowing the internals, without knowing the nitty-gritties, to businesses who actually go on and deploy those systems. For example, Amazon, Google, Netflix, all of these Fortune 500 companies. And finally, all the way to users who are the most impacted by the decisions that are being made by the AI systems, right? So explainable AI has 3 primary goals. The first one is to detect any instances of bias and discrimination in the model's outcomes and processes. The second is to provide to end users actionable insights to change model outcomes in the future. And the third is to enable practitioners, machine learning developers to enable debugging these algorithms and models, right? So let's take a look at an example here. So this is a very popular data set that has been used in fair machine learning literature. And the instances, the rows are your individuals, information on their age, their demographic information, and financial and educational background. And the idea is then to use a machine learning model, train the model on top of this data, and predict whether or not they're making less than or more than 50,000 annually. And it turned out that such a model built upon publicly available data sets was found to be heavily biased against females. And we have a way to capture this bias. We have a way to quantify this bias, taking advantage of our legal talk about demographic parity, disparate impact, and boiling all of that down to mathematical statistical properties, we are able to quantify that bias, right? So now let's say we have a system that gives us a particular amount of bias. Now, how can we debug the system? How do we understand why the model exhibits this kind of unexpected or discriminating behavior? And that is the question that we are interested in right now. Right? There have been a lot of popular explainable AI techniques that are mostly feature-based explanations. They look at, your model is deeming your age as the most important, or your model is deeming the checking account as to be the most important. If you have more in a checking account, you are going to earn more, and things like that. However, these and Lime and Shapley, these are very popular techniques. However, these do not capture any correlation. Sorry, these capture correlation between the input, the features, and the target variable. They cannot explain why there is any bias in the model. Okay? And it turns out that a lot of times your model bias can be attributed back to the data that it has been trained upon. Okay? There could be different instances of bias in your data. For example, there might be historical bias in the data that you have trained it upon. Okay? There might be a selection bias. You might have chosen the wrong data sets to work with. There might be a class imbalance in your data, and data poisoning attacks, and so on and so forth. How can we debug such sources of model bias? So in this work, what we have come up with is Gopher, which is a system that traces these instances of unfairness back to the model and back to the data that it has been trained upon. So we have come up with notions of root causes of bias and causal responsibility, where we say that a data instance or one row, this part of the data is responsible for your bias if by removing that data and training the model, you would have reduced bias. Okay? And then we quantify the contribution of such a subset by what we call as causal responsibility. Now, how do we measure that? A very naive way is to remove each instance, retrain the model, and observe what is the updated fairness metric, or what is the updated quantification of bias. Right? And in this case, we saw that it went down from 20% to 18%. The closer we are to 0, the better. So that by removing that instance, Matt, by removing that instance in our data, we have reduced our bias by 2%. So the contribution of that instance was 2%. It was responsible for bias. And we said that that data point is a root cause of bias. Okay? That's an idea, but you can imagine we cannot do this for every single data point. That is going to be exhaustive because we might have a large data set, or we might have a very complicated neural network, a very complicated model that takes hours to retrain. We wanted to efficiently compute this change in the fairness metric, and to do that, we were lucky to borrow concepts from robust statistics, something called as influence functions. What influence functions let us do is that they let us estimate what is the change in model parameters without even retraining the model. Okay, so for each data point, we can estimate that if we remove it, this is how my model fairness, model bias is going to change. Right? Now imagine you show all of that to a machine learning practitioner. So circling back, we are generating these explanations, we are generating these instances, these root causes of bias for your machine learning practitioner to help them understand what is causing bias in my system. Okay? Now that practitioner has identified that, okay, there are these 100 instances that are the most responsible for bias in this model, but how do they make sense of it, right? So it is not possible to understand that, hey, these 100 data points had the most impact on bias. If you remove them, your bias is going to reduce by the max. So we came up with another idea that instead of showing them these 100 instances, could we summarize them? Could we have a better representation? Could we generate interpretable explanations? For example, saying that, in this data set, the subset that has the predicate gender is male is the most responsible for bias. Okay? And imagine we can do this by using influence functions. We can use this by first order influence functions, which is taking a single derivative, or we could use group influences, which takes the correlation between your different data points. Okay, so these are again from your machine learning conferences, and we were lucky to find out that, okay, we now know how much each of this subset will contribute to bias. However, we still have a problem that the clicker does not work, and it works, but we still have a problem that we have to compute the responsibility of a lot of subsets, right? Which becomes exhaustive. We cannot keep on doing that. So what we do then is that we build a lattice-based subset retrieval that borrows from concepts in association rule mining way back in 94, 30 years ago. So the idea is that we build a lattice of these different predicates, and at each level, node is built by merging from two nodes in the previous level, right? However, by doing this, we are not reducing our search space, but we can use smart pruning techniques. The first one is pruning on the basis of support threshold. We say that we are only interested in data in subsets that have at least this much of data, at least 5% of data points, right? By doing that, we are able to prune a huge part of our data. The second pruning rule is something called as interestingness. We say that, okay, we are only interested in a node if it is going to reduce our bias by much. And the idea behind this is that when we go deeper in this lattice, there are going to be more predicates at each node, right? They are less interpretable. And if you're going deeper, then being less interpretable has to be justified by some impact on bias. So for example, here saying that this node where gender is male and marital status is married, that has an interestingness of 0.63 compared to its parents, which had higher interestingness. If we remove those, that would be more effective, but that small subset is not giving me much information. Okay? By using these two pruning rules, I'm able to prune, or I'm able to get away with a lot of subsets. We have a very few subsets left, and we can compute their causal responsibility using group inferences, right? And finally, we rank them down in decreasing order of their impact on bias. What did we achieve? This was another data set that has similar information, users, individuals, demographic, and financial information. And the idea is to predict whether or not somebody would be given a loan, if they are a good credit risk or a bad credit risk. It was found that this data is, again, heavily biased against younger population, right? And we were interested to learn what happened wrong with this data? Why is this data biased toward one section of the society? What we found was that these are the top three explanations. The first explanation that has 5% of data, right? If we remove that particular subsection from our data and retrain our model, we would be able to reduce our bias by more than half. Okay, so that small fraction of data, 5% of data, is responsible for 55% of my bias. Another subset that has slightly more amount of data, even that reduces my bias by more than a third, right? So these are very small fractions of data that are contributing to our bias a lot. Okay? And these explanations are diverse. There is minimal overlap between the data instances that are part of these subsets. And we also have looked at, we don't want to remove the data points, but instead, let's say, can we just update them? We have worked on that. There are details in the paper. They are long and boring, but even by updating, we can reduce the bias by much. So that's the overview of the system that we have developed, and it's called Gopher. It generates compact, interpretable causal explanations, causal in the sense that if we remove the data points, if we remove the subsets, we are able to reduce bias, right? We are able to identify these coherent subsets. We exactly know that they can be shown in the form of first order predicates, and we are able to generate top K patterns that are responsible for your model bias. So taking this idea further, we are working on bias and fairness and trust in this the entire data science pipeline, right? So where we no longer have just data and a model and output, but we have raw data, which is messy. We want to clean it. We want to acquire better data. We want to integrate the data, do a lot of stuff with the data, finally feed it into the model, right? And then let's see what is the bias of the system, right? So we are working on operationalizing fairness and transparency in the entire data science pipelines. And we are looking at these different questions, which are all work in progress. And that's all for my talk. I would be remiss if I don't thank my awesome grad students and my awesome labs and my funding agencies. Thank you so much. If you have any questions, I would be happy to take them unless the organizers kick me out. Okay. Thank you so much.